Hi, today we'll learn Quicksort. In this video, we'll talk about three things: why it's called Quicksort, how it works, and its implementation. And then we'll discuss its time complexity and how we can improve it. Without further ado, let's get started. Quicksort is an in-place sorting algorithm that uses divide and conquer strategy. It gets its name from its inventor Tony Hoare, a British computer scientist in 1961. When implemented well, it can be faster than its main competitors, merge sort and heap sort. Now let's see how it works. Here we have an array, 4, 8, 7, 5, 6. And we'll sort the array in non-decreasing order using Quicksort. So in the end, it should be like this. Before we start, we need to understand what is partition, because Quicksort recursively breaks down the original problem into subproblems by partition. And partition begins with the pivot. So what is pivot in an array? Pivot is just an element in the array. And all the elements to the left of the pivot are smaller than the pivot, while all the elements to the right of the pivot are larger than the pivot. Elements equal to the pivot can go either side, and in this video, we put them on the left. Let's understand pivot with this example. Here's an array. 6 marked with yellow is the pivot, because all the elements to the left marked with gray are less than or equal to 6, while all the elements to the right marked with green are larger than 6. Alright, now we know what is pivot. Then what is partition? Let's understand it with this little comic. Here's an array, and then we choose an element randomly. We choose the last element, 6, as our pivot. Note that it's not a real pivot yet. Now we apply our secret weapon, partition. Then all of a sudden, the array is rearranged. And the result is that all the elements to the left of the pivot are smaller or equal to it, while all the numbers to the right of the pivot are larger than it. In other words, partition is actually the function to rearrange the given array so that the left subarray is less than or equal to the pivot we choose, while the right subarray is larger than the pivot. We can implement the partition function however we want, as long as it rearranges the array this way. Okay, let's start the real game. Here's our array, 4, 8, 7, 5, 6. We need to quicksort this array in non-decreasing order. First, we choose a pivot. It can be randomly chosen, but in this video, we always choose the last one. So 6 is chosen as pivot. Left pointer starts with the first element, and it moves to the right. Left pointer alarms when it sees an element not smaller than or equal to the pivot. Right pointer starts with the last element excluding the pivot, and it moves to the left. Right pointer alarms when it sees an element not larger than the pivot. Left pointer works first. It points to 4. 4 is smaller than pivot 6, so it moves to the right for one step. Now it points to 8. 8 is larger than pivot 6, so it alarms and freezes there. Now the right pointer starts to work. It points to 5. 5 is smaller than 6, so it alarms and freezes there. Now we check if the left pointer crossed the right pointer. The answer is no. So we swap the two values, 8 and 5, and both pointers move for one step. Again, the left pointer works first. It points to 7. 7 is larger than pivot 6, so it alarms and freezes there. Now the right pointer starts to work. It points to 7, which is larger than pivot 6, so it moves to the left for one step. Now it points to 5. 5 is smaller than pivot 6, so it alarms and freezes there. Now we check if the left pointer crossed the right pointer. The answer is yes, so both pointers stop. We swap the pivot 6 with the element pointed by the left pointer, and the partition is done. After partition, we get a left subarray and a right subarray. Our pivot 6 is already in its ultimate right position. Next, we partition the left subarray. We choose the last element 5 as pivot. Left pointer and right pointer both start with element 4. Left pointer works first. It points to 4. 4 is smaller than pivot 5, so it moves to the right for one step. Now the left pointer crossed the right pointer, so both pointers stop. We swap our pivot 5 with the element pointed by the left pointer, and the partition is done. Our pivot 5 is already its ultimate right position. The left subarray has only one element, 4, and the right subarray is empty. We partition the left subarray first. It has only one element, therefore it is considered sorted, so there's no need to partition it. 4 is now in its ultimate right position. Same reason, there's no need to partition the empty right subarray. Now we need to partition the right subarray 8, 7. We choose the last element 7 as pivot. Both left pointer and right pointer start with 8. Left pointer works first. It points to 8. 8 is larger than pivot 7, so it alarms and freezes there. Now the right pointer starts to work. It points to 8. 8 is larger than 7, so it moves to the left for one step. Now the left pointer crossed the right pointer, so both of them stop. We swap the pivot 7 with the element pointed by the left pointer. Now our pivot 7 is already in its ultimate right position. The left subarray is empty, and the right subarray has only one element, 8. Neither of them needs a partition because they are considered sorted, so 8 is now in its ultimate right position. Now the whole array is sorted, and the above process is how Quicksort works. Note that the partition process we showed you is just one of the many ways to reach the same result. Now let's talk about how to implement Quicksort. We start with pseudocode. Given an array, first, we check the array length. If the array length is 0 or 1, then we do nothing because it's considered sorted. Otherwise, if the array length is larger than 1, we first partition the array. After partition, the pivot is in its ultimate right position. And then we call the Quicksort function to deal with the left subarray and right subarray subsequently. So it comes to the implementation of the partition function. First of all, we need to choose a pivot. In this video, we always choose the last element as pivot. Then we use 2 pointers to go through all the elements. The left pointer starts with the first element, and it moves to the right. The right pointer starts with the last element, excluding pivot, and it moves to the left. The left pointer works first. If it doesn't cross the right pointer and if it points to an element smaller or equal to the pivot, it will move to the right for one step. Left pointer keeps moving until it sees an element that breaks this rule, or if it crossed the right pointer. Same with the right pointer. If it hasn't crossed the left pointer and if it points to an element larger than the pivot, it will move to the left for one step. Right pointer keeps moving until it sees an element that breaks this rule, or if the pointers cross each other. Anyhow, both pointers will stop at some point. At that moment, check if the pointers crossed each other. If the pointers haven't crossed each other yet, we swap the elements pointed by them and start over the whole process until they cross each other. When they cross, both pointers stop, and we swap the pivot with the element pointed by the left pointer. Then partition is done. After partition, the pivot is in its ultimate right position, and we have successfully divided the input array into left subarray and right subarray. Once we understand the pseudocode, we can implement it in any language. In this video, we used Python, and here's the code. The input is an array with real numbers, and since Quicksort is an in-place sorting algorithm, there is no need to return anything. Now we understand what is Quicksort, how it works, and how to implement it. Let's talk about the time complexity and its optimization. Let's say the array length of the input array is n. Then what's the time complexity for quicksorting it? For a short answer, I listed the best case, average, and the worst case time complexity of Quicksort here, and we'll show you how to calculate them one by one. Let's recall our pseudocode. Based on this pseudocode, we can draw a tree like this. The tree branch stops when it sees an input array with only one element or empty. In the worst case, after each partition, one of the subarrays is always empty, as shown in this example. This tree shows the whole process of quicksorting array 5, 4, 3, 2, 1 in the worst case. For convenience, we use Pn to represent the time it takes to partition an array with n elements. We assume Pn equals c times n. C is some constant, because we need to go over every element in order to partition the array. It is reasonable to assume that the time it takes increases linearly with the array length n. Last, we assume P0 equals P1 equals c. Alright, now let's calculate the time it takes to quicksort the array in the example. All we need to do is to sum up all the nodes in the tree. So it can be written like this. Let's rearrange it, and it's like this. Then we get the final result. Now let's think about the general case. The time it takes to quicksort an array with length n, according to the example above, is like this. Since this is an arithmetic sequence, the result is like this. When n approaches positive infinity, we can use n squared to describe the time it takes to quicksort the array. So the worst case time complexity is big O of n squared. Now let's talk about the best case scenario. In the best case, after each partition, the left subarray and the right subarray have almost equal number of elements, like what is shown in this example. And this tree shows the whole process of quicksorting array 5, 4, 3, 2, 1 in the best case. To calculate the time complexity, we have the following assumptions. For convenience, we use Pn to represent the time it takes to partition an array with n elements. And this time, we focus on each level of the tree. And all we need to do is sum up all the nodes in the tree. And the sum is like this. After rearrangement, the final result is like this. Now let's consider the general case. Assume the length of the array we need to quicksort is n. Then the time it takes to quicksort this array is like this. And with some rearrangements, it is like this. When n approaches positive infinity, we can use n log n to describe the time it takes to quicksort the array. So the best case time complexity is big O of n log n. Last but not least, let's discuss the average time complexity. For convenience, we use Pn to represent the time it takes to partition an array with n elements, and use Qn to represent the time it takes to quicksort this array. In this example, the average time it takes to quicksort is like this. The first term is P5, which represents the time it takes to partition the array 5, 4, 3, 2, 1. In the second term, 1 over 5 means the possibility of us choosing the number 1 as our pivot, and Q0 plus Q4 means if we indeed choose 1 as a pivot, then this is how much time it takes in total for the quicksort. Same with the third term, it represents the time it takes if the number 2 is chosen as the pivot. The list goes on and on until we tried all the possible pivots. Now let's rearrange the terms and it will be like this. So in general, the time it takes to quicksort an array with length n can be written as this. From here, we can use some math. If you're not interested, you can skip this calculation and just remember the average time complexity is n log n. But here's how we calculate it. This is what we have. We copy it once and name it equation 1. Then we use n-1 to replace all the n's and get equation 2. Subtract 2 from 1, we get this. When n approaches positive infinity, the constant c can be eliminated. So we can rearrange the equation into this. We copy it once and then we replace n with n-1, n-2 all the way until n equals 1. We sum up all the equations and we get this. This is called harmonic series, and according to Euler, when n approaches positive infinity, the sum equals the natural logarithm of n plus gamma. Gamma is called Euler-Mastroianni constant, and it's less than 1. So the whole thing is less than this. As n approaches positive infinity, all the constants can be eliminated. So we can use n log n to describe the time it takes to quicksort an array with length n. Therefore, the average time complexity is big O of n log n. Alright, we're done with the time complexity. Now let's talk about optimization. The most important thing is to choose the pivot wisely. Let's recall our tree. In the best case scenario, we always choose the pivot whose value ranks in the middle, while in the worst case, our pivot is either the largest or the smallest element. So how to avoid the worst case scenario? Assume the elements in the given array are distinct. Then there are two ways we recommend. First, we can randomly choose a pivot every time, and the chance for us to get into the largest or the smallest element is 2 over n. When n is large enough, the chance of running into the worst case is very rare. Another way is to choose pivot from the first, middle, and last element in the array. We compare their values and choose the one whose value is in the middle, like what is shown in the examples below, so that we can avoid the worst case. However, when there are many duplicates in the array, for example this one, then these methods may not work. So it's always a good idea to choose the sorting algorithm based on the characteristics of our input array. So thanks for watching. Please like this video or subscribe to our channel below if you'd like to support our work, and we'll see you in the next video.